Hello everyone and good morning. Welcome to the OneClass channel. My name is Fejiro. I'm an honors Bachelor of Science graduate, currently working towards medical school. Today I'll be doing my best to go over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or tutoring, or just further clarification on the topics we covered today, please check out the links in the description below so that way you can get some nice professional help offered by one of our tutors here. With that being said, let's hop right into the session for today. And we're going to start with question number 1. What is the molar mass of glucose? Okay. So we have question 1 for today. Molar mass of glucose. So for these type of questions, the good news is that they did give you its the formula, the atomic formula here. Okay, C6H12O6. It's important to find the molar mass that you add of the atomic mass units of every constituent. So as you can see here, for glucose, it says that we have 6 carbons, okay, and we have 12 hydrogens, and then we also have 6 oxygens, okay. So with that, we would actually go to our periodic table. It's important that you use the periodic table given to you, or at least if you weren't given one, make sure you keep using the same one and you're constant with it, because some periodic tables do vary slightly on the atomic mass units, and it's just important to be consistent. So we'll start with the carbon, okay? We have 6 carbon. So the carbon's atomic mass unit is 12.011, okay? Hydrogen is 1.008, and oxygen is 15.999. Alright, so I put the multiplication there is because I want to do 6 of the 12.001. So for glucose, that means carbon would contribute of its whole molar mass 12.011 times 6. So we have 72.066. That is how much all the carbons in glucose contribute. Hydrogen, we would now multiply the 1.008 times 12. That would be 12.096. And then we do the same thing for the oxygen, 15.999 times 6. And that would be 95.994. Okay? And here is where we would add them all up together so we can get our total molar mass, because now we've factored in every constituent in glucose, okay? So that's plus 12.096 plus 72.066. So the total we get for glucose when we add them all together is 180.156. But we're not done yet, because the molar mass, this is a representation of how many grams typically per 1 mole of the substance. And 1 mole of glucose, as we've covered, has 6 carbons in it, 12 hydrogens, and 6 oxygens. And the reason why I mention this is because the units are important here. It's not just going to be just this number. We have to put the units of grams per mole. This right here is the molar mass of glucose. It would not be the molar mass without the units, because this is what we would be using if they said find, for example, the moles of glucose based on this mass. You would need the molar mass to be able to convert it from moles to the grams, or grams to moles, and vice versa. So with that being said, we'll look at our choices here. As I said earlier, the periodic table does vary, so it's important to pick the answer that's the closest to it. So based on the choices we have here, the molar mass of glucose, the best answer would be E. Okay, the 180.00. Only because it's the answer that's the closest that we can pick from. How did they get it? What they probably did here was they rounded the carbons to 12, the hydrogens to 1, and the oxygens to 16. Only because of the fact that, considering that some periodic tables do have that, they would have carbons, atomic mass units of 12, hydrogen would be 1, oxygen would be 16. And if you just did the same thing and multiplied it, you'd get 72 plus 8 plus 16 times 6. Whoops. It's 12 hydrogens, sorry. 72 plus 12. And exactly, you do get exactly times 6 times 12 times 6. So that would be, you do actually get 72, 12, and 96, and all this does indeed add up to exactly 180. So that's most likely what happened here. But let's see what we have in terms of what our professional, how they solved it. They did have carbon, they said 12 units, hydrogen was 1, oxygen 16, and they multiplied the constituents like we did up here, and then exactly that's how they got 180 grams per mole. So once again, I do stress it's important to go through the periodic table and just be consistent in the one you've selected, because for these type of questions, even though you may not get exactly the answer, you should always fall really close to the correct one based on the periodic table you're using. So now let's move on to question number 2. We have here, what is the Lewis structure for H2PO4? And if necessary, expand the octet on the appropriate atoms to lower formal charge. So with this, the way I like to solve these questions is I actually like to solve what the, and it's interesting here because they use H2PO4 because typically, Lewis structure of H2PO4, because if we actually were to try to separate it by the ions, the cations and the ions, you'd first recognize that this is an acid, but this is not really complete because the PO4 that I'm familiar with is PO4 3 minus. This is a phosphate ion. Okay, that is what we have there. And if for this, in order to have a neutral charge, is maybe what it's implying, it would actually be H3PO4, and this would be phosphoric acid. But nonetheless, let's assume that we're actually trying to solve H2PO4. So for this, we would actually first, I do recommend starting out with the phosphate ion. But instead of doing a phosphate ion, I'm going to do a theoretical one because based on this, we're dealing with a PO4 2 brightest. Okay. With that being said, let's just go through it. Phosphorus, okay, based on the periodic table, that is on the 15th column. So that's 5 electrons it can donate, okay? So that would be 5. Oxygen is on the 16th column. So that's 6 electrons it can donate. But there's 4 of them. So that's 6 times 4. That's 24. And then we have 5 and 24. But then we have this 2 here. This right here, because it's a negative, it actually implies, or actually states, that this whole ion is getting 2 more electrons, okay? So, with that being said, we have 5 plus 24 plus 2, okay? And we have a total of 31 electrons. Let's see if we can balance this out. So, we'll put phosphorus in the middle because it's the only unique one. And we're going to try to get it to have 4 oxygens. So we have 1, 2, 3, 4 bonds so far. And that would be oxygen, 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 oxygen. Okay. So let's start with the oxygens. Oxygen right now is sharing 1 of its 6 electrons. So 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And 2, 3, 4, 5, 6. And phosphorus, on the other hand, is right now sharing, just make sure I'm counting this correctly, it's sharing 4 of its 5. So we just have an extra one there. Okay? But now we have the 2 minus. Okay? So that means we want to now add 2 more electrons. So we're going to add it to 2 oxygens just to fill the octet rule. 1, 2. Okay? So that's what I've done there to balance it out. So now 2 oxygens have finished their octet rule, but there's still oxygens that are very incomplete. So, with this being said, we're going to do here to be able to get the PO4 2 minus. We're going to now, right now we're going to count how many unpaired electrons we have. We have 1, 2, 3. Okay? So, in order to be able to balance this out, we need to at least make one of the unpaired electrons bond appropriately. Okay? And they would actually come together to form a double bond. So if we redrew this, we now have phosphorus with the 2 oxygens. And this one here. Okay? And then we have the double bond right here. Okay, and we have the oxygen with this one lone pair. All right, and that is what we have currently. But then we still have this one lone pair. This one unpaired electron, which is why PO4 2 minus, unfortunately, just doesn't work. The reason being is because the fact that that's why phosphate ion needs the PO4 3 minus. I just wanted to work through this to show you why this wouldn't balance out, is because as we've shown here, we have literally 1 unpaired electron. Okay, and the reason why I say this doesn't work is there's nowhere you can put this 1 unpaired electron to where this molecule itself isn't unstable to the max. So the why I've done this is because I do think that this right here is a typo, and we actually want to draw the Lewis structure of H2PO4 minus. The reason why I say that is because the fact that if you add in 2 hydrogens to PO4 3 minus, that's how you get 1 minus left. So this would be a hydrogen dihydrogen phosphate ion. That is what we should be solving here. So now let's go back to this, what we're drawing here. If now we're dealing with 3 minus, so we've added 3 electrons, we can actually complete this octet rule by adding the last one right there, okay? That's PO4 3 minus, okay? And so now with this being said, it's actually quite easier now to add the 2 hydrogens. Because remember, these hydrogens are protons, they're just H pluses. You can actually throw them specifically into any part that has a formal charge of -1. And the reason why I'm mentioning formal charge is because, as you can see, the hydrogen here, hydrogen plus, this thing already has a formal charge of +1. So it wouldn't just go to parts that are neutral, it would go to -1. Now, to be able to find out the formal charge, we look at things like phosphate, for example. Its natural state, it would be like that, okay? 2 electrons and 3 bonds. But these 2 electrons can actually serve as other bonds because it has an expanded octet rule. And as you compare to the phosphate here, it indeed has 5 bonds total. Oxygen, on the other hand, alright, is normal sense because it has 6 valence electrons. It's like that. 2 lone pairs and 2 bonds, which is what happens here. So that one has a formal charge of 0. But these 3 oxygens here, instead, they have 1 lone pair and 3 bonds. So in order to do that, they would have to gotten rid of the bond and added the lone pair. In order for that to happen, it needs to take a step into a negative formal charge. That is a -1 formal charge there for oxygen. So each of these 3 oxygens has -1 because they have 3 lone pairs and 1 valence electron. So that's where the hydrogens will go. It doesn't really matter where, but we know the 2 hydrogens, well, 1 each will go into the part where it's -1 formal charge. So you have a hydrogen that sticks right there and a hydrogen sticks right there. Okay, and now we can redraw this correctly just with bonds to be able to write down the whole dihydrogen phosphate ion. Okay, and I will stress it as a phosphate ion because, as we said, those 2 hydrogens will not cancel out the charge. Now, as you can see here, the ones that were attached to hydrogen now have a formal charge of 0 again because they have 2 lone pairs and 2 bonds, which would be the one described right there. Okay? So now we've drawn the Lewis structure and we did expand the octet on the phosphate ion, and that is how we were able to lower the formal charge because now the phosphate has 0, the oxygens all have 0, and the only one that doesn't have 0 would be this oxygen here, which has a formal charge right now of -1 because it has 3 lone pairs and 1 bond. And this thing can experience resonance because this formal charge of -1 could happen at this oxygen, which means the hydrogen would have gone over here, or it could have happened here, which means the hydrogen could have gone over, which means this hydrogen could have gone over here as well. It's only in one spot though. So if I were to quickly rewrite this, the other resonance structures would look like PO, not this, yep, and then OH. In fact, this double bond here could actually even move through it. So this one could actually be no longer the double bond. It could be like this. This is just one example of a possible resonance structure because now our formal charge is on this oxygen here. Okay. The important thing though is that however you draw it, just make sure that you're not breaking any octet rules except for the ones that can't have expanded octet rules, because that should be able to lead you to the answer. But we're just going to hide this one. This would be the Lewis structure of H2PO4 minus, and I will stress it's an ion. This is not a neutral molecule. It does have a charge. It does not have a net charge of 0. So as you can see here, the way they've drawn it, they have, this is actually going to be a as we discussed earlier, H3PO4, phosphoric acid. You can see that because we have 3 hydrogens and 4 oxygens. So this is H3PO4, okay? And then this is an expanded octet, and this right here, the B, is an octet that's not expanded. So what they did is that they shifted one of the bonds on the double bonds out to the oxygen, okay? So what they did was like this. This one is with the hydrogen, and this is for H3PO4. So this is for phosphoric acid, okay? Which is why they have 3 hydrogens there. But the reason why they were able to do now that is because, as you can see, phosphorus went from 5, or actually, technically, if we redrew it as 2 lone pairs and 3 bonds, it went from that to 4 bonds, okay? And when you replace a lone pair with a bond, now you're going the opposite way, as it's no longer now you're adding electron, you're taking it away. So this formal charge is actually a +1. And you can see here how we have now a +1 -1. And also the cool thing is that this still, for phosphoric acid, still has a neutrality, a net of 0. It is still going to be a possible form of phosphoric acid. It's just more unstable because, as you can see here, there is more of the formal charges that are not equal to 0. In fact, if I went ahead to now try the dihydrogen phosphate, which is what we were solving, the H2PO4, we would actually have like this, where we'd have a -1 here as well. This still would be in total H2PO4- as we discussed, but this right here is more unstable than the one over here. This is the most stable. The starred one is the most stable because here there's a lot more of the formal charges that are not equal to 0. These two should reorganize to where they would cancel out their formal charge. So that's why B, as seen in this picture, would actually be more unstable than A. Okay? And exactly as I said, the compound A is more favorable in this case. And as you can see, even in this answer here from my colleague, they did draw H3PO4 and not H2PO4. Because H3PO4 is the one that has a net charge of 0, but H2PO4, as I discussed, would be the minus, H2PO4-. So nonetheless, this is correct. All right, let's move on to question number 3. For question 3, we have, what is the Lewis structure of NH2Cl? Okay. So, in order to solve this, we would first approach it using the periodic table just to find out how many electrons we're working with. We have 1 nitrogen, 2 hydrogens, and 1 chlorine. So nitrogen, okay, is on the 15th column, so it would donate 5 electrons to the cause. Hydrogen, 2 electrons, and chlorine, well, sorry, I skipped over it because I'm used to it, but hydrogen, the reason why I said 2 electrons, because each hydrogen is on the first column, and there's 2 of them. So that's 1 electron each, which is how we have it contributing 2. And chlorine is on the 17th column, so that would be 7 electrons. And there's only 1 of them, which is why we only did 7. So 5 plus 2 plus 7, that is 14 electrons total that we're working with for this Lewis structure. Now, we're going to put nitrogen and not chlorine in the middle because nitrogen has the most unpaired electrons, okay? And now we're going to draw out the bonds. So we have H, H, and Cl, okay? We could have drawn it, or H down here and a Cl over here. It does matter in terms of the stereochemistry and how it orients itself, but we're just going to use this one for example, okay? So, with that being said, this is what we have currently. And then we're going to fill out the octet. So hydrogen is already sharing 1 of its 1. It's complete. Nitrogen, as I've added those 2 electrons, it was sharing 3 of its 5, and then we have 4 and 5. Chlorine was sharing 1 of its 7. So we have 2, 3, 4, 5, 6, 7. Okay? So, with that being said, we're going to make sure we have the right amount of electrons. We have 3 bonds, so that's 6 electrons right there, plus this lone pair of nitrogen, that's 8 now total. And then we have plus 2, plus 2, plus 2. So that's 8 plus 6. We do have 14 electrons. Okay? So perfectly done. Now if we go through really quick and establish its formal charge, nitrogen is indeed in its preferred natural state of what it would be for formal charge of 0. Chlorine as well is in its preferred state of a formal charge of 0. And hydrogen, same thing. Okay, because it has 1 bond on hydrogen, 3 bonds, and 1 lone pair of nitrogen. Oops, Yeah, and 3 lone pairs and 1 bond on chlorine. Okay. So with that being said, this will be the preferred Lewis structure for NH2Cl. Let's see how we did. So we do have 14 electrons. That's what we want. And then they drew it out, and then they hopefully filled in the electrons, and there we have it. We have now the balanced Lewis structure for NH2Cl. And then they also calculate the formal charges as well, and they're all 0. Perfectly done. And this is correct. All right, now let's move on to question number 4. We have how many of each atom are there indicated in the formula of aluminum sulfite. Okay, atoms in aluminum sulfite. So now in this question, they have already given us the molecular formula, but if they hadn't, let's just visualize how we would go through this. So the key thing here is that luckily for us, we do know what aluminum is. It's our cation in this case. So we refer to the periodic table and we see where it is. It's on the 13th column. So we know that alumina would be Al. Because of the 13th column, we have it that it has 3 valence electrons. So the easiest thing for it to do will be to get rid of those 3. So that's why we have Al3+. That would be the aluminum cation. Okay? So now sulfite, this one's a lot more trickier because unfortunately you do have to memorize these because there's different types of ites and ates anions. So for example, I personally like to start with sulfate and then work from there. So the sulfate ion, based on what I memorized, is SO4 2-. That right there is sulfate. I'm going to write it here so there's no confusion. Okay. In order to go from sulfate to sulfite, the rule is actually that you subtract 1 oxygen. So that's why I like to start with sulfate, because it's, to me, the easiest one to memorize at first. And then when you start changing the suffix, you can kind of know what steps to take from there. So the sulfite ion will be -1 oxygen. So it'll be SO3. But here's the part that's important. The charge stays the same. 2-. This is an aluminum sulfite ion. Okay. So now in order to balance out the charges, we need the least common multiple, because right now we have a 3+ and a 2-. Okay. We need something to where they can both cancel out each other out total. So the least common multiple here is 6. So we would need then 2 of the aluminum and 3 of the sulfite, because in total we should get 6 positive charges and 6 negative charges. Okay. So then now if we were to rewrite this, hopefully we get the same formula as what they said in the beginning of the question. We have now Al2, SO3, 3. And let's see here. Exactly. Al2, SO3, 3. Perfect. Okay. So now they actually are asking how many of each atoms are there indicated. The cool thing about this question is that this is actually the step you would take before you solve for the molar mass, because you would then add the constituents of each atom, like how many atomic mass units each atom contributes. So if we looked at this, as we've now solved it, we have 2 aluminum. Okay, so that's 2 aluminum in there. And in here, we have to make sure we multiply inside. So to both atoms in there, we would then say we have 3 sulfurs. Okay. And here, this is why you have to multiply both in the inside. It's not 3 oxygen. It's not 6 oxygen because we're adding. We're multiplying 3 times 3. So we have now 9 oxygens total. Okay. So in regards to this question, how many of each atoms are there indicated in the formula? We would say 2 aluminum, 3 sulfur, and 9 oxygen. And that is actually what they say here. As you can see, 2 aluminum, 3 sulfur, and 9 oxygen. Now let's move on to question number 5. For this question, we have what is the Lewis structure for the oxygen molecule, okay? For O2. And the reason why the oxygen molecule is O2 and not just O is because in nature, oxygen likes to bond with itself, and that is just one of the examples of anions typically like to bond with themselves, so nonmetals, to be able to be more stable, okay? And that's actually what we would refer to as oxygen gas that we actually have floating around us, what plants produce. This right here would be what they're referring to, not just oxygen by itself, but O2. That's why they specifically say oxygen molecule and not oxygen atom. If they said oxygen atom, we would really just be drawing the Lewis structure of a single oxygen atom. So now we're going to do the oxygen molecule. So we actually have each oxygen, because it's on a 16th column, would contribute 6 electrons. So in total, we're dealing with 12 electrons, okay? And now, let's just draw it out. We have 2 oxygens bonding to each other. That's what we're going to start with. And so far, these oxygens are sharing 1 of its 6 electrons. So it's going to be 2, 3, 4, 5, 6 on this side, and 2, 3, 4, 5, 6. And the reason why I drew it like that is because, as you can see, there's 2 unpaired electrons, 1 in each oxygen. So to really balance out, what they're going to do is that they're going to actually send them over here to create another bond in between. So this would actually end up looking like, let me just draw a little bit bigger. Like that. This right here would be our oxygen molecule. And now to check its formal charge, oxygen typically likes to have 2 lone pairs and 2 bonds. And the double bond does count as 1 bond each. So that's how we can actually verify these 2 have a formal charge of 0. They're actually content with this form. They also satisfy the octet rule. And if we actually counted how many electrons we had here, it should equal 12. Each bond does have 2 electrons in it. So that's 4 electrons from the bonds, and then 6, 8, 10, 12. So we have satisfied every situation and position we put ourselves in. And this will be the Lewis structure for O2 molecule. That is what it should look like. And there we have it. There's a double bond there, and it has 2 lone pairs on each oxygen. So this is correct. Now let's move on to question number 6. We have here, what is the Lewis structure of HCO2? So this would be hydrogen carbonate ion. And the reason why I say that is because HCO2 minus, okay? So we're going to assume that it's referring to HCO2 minus and not HCO2 minus. That would be a little bit more complicated. So what I like to do, the reason why I say hydrogen carbonate is because what usually helps me is I like to separate the hydrogen typically from the molecule, because what we're really dealing with is just a carbonate ion and a hydrogen ion, or just a proton, okay? So how do I know this is carbonate? Just as a quick review, okay? So carbonate, that would be known as CO3 2 minus. This is carbonate, okay? CO2 2 minus is carbonate, okay? This is how I can name it as hydrogen carbonate ion. Just as a quick nomenclature review, just really get familiar with your ions, okay? So now with that being said, we're actually going to now first just solve the Lewis structure of this one here. So it has 2 minus. So we have here, okay, carbon is on the 14th column, so that's 4 electrons it can donate. And oxygen, that's 6 valence electrons times 2, so that's 4 plus 12. And then we have the charge of minus 2, okay, which is how we have 2 more electrons, all right? So in total, we need 18 electrons in this carbonate ion. So we have now C, whoops, CO, O, okay? So that's what we're going to start with here. And now we're going to fill out the rest of the octet rule. Oxygen, 3, 4, 5, because it's now sharing one of its 6. Same with this one, 1, 2, 3, 4, and then 5 there. And carbon right now is sharing 2 of its 4 electrons. So 1, 2, 3, 4. That will be it for this one. But as we discussed, we actually have 2 extra electrons. So what I'm going to do here in this case is, just to make sure that we can do this perfectly, I'm going to add 1 electron here and 1 electron there. Okay. The reason why this has been done is because we need to set this up in a way to where the octet rules are filled, and also we've now, I guess, adjusted for every I guess situation here. So just to make sure, now we should have 18 electrons. Let's quickly count through the double bonds. I mean, the bonds have 4 electrons: 6, 8, 10, 12, 14, 16, 17, 18. So perfect. All right. So now let's actually go ahead and now throw this one here. Oops. These two form a double bond. Okay. And so now we have carbon like that. It has a double bond here and a single bond there. Okay. And just to make sure, 1, 2, 3, 4, perfect, following the octet rule. And now the oxygen as well is going to be like that. Okay. So with this being said, now let's actually make sure we have the right formal charges, because this will actually help us determine where we put the hydrogen. Okay. So we would have, as you can see here, carbon. Well, actually, let's start with the oxygen on the left. Or it doesn't really matter. This will be the neutral formal charge for oxygen. 2 bonds and 2 lone pairs. Okay. So as you can see, only this oxygen really follows that. So this one we can say that has a formal charge of 0. So it won't write anything. But this oxygen here has instead 3 lone pairs and 1 bond. When you replace a bond with a lone pair, you go into the more negative side. You've added an electron. So this one here is actually going to be -1 for the formal charge. Okay. And now the carbon, all right, usually wants to have 4 bonds, 0 lone pairs. Once again, similar to the oxygen, it's gotten rid of a bond and added a lone pair. So that right there would actually be a formal charge of -1 as well. Okay. So the hydrogen is a plus. This hydrogen will be able to go into either the carbon or the oxygen to be able to now balance this out. But here's the issue though. If we actually now look at the electronegativity, or typically things that like to add electrons, just be able to make the most realistic thing. Carbon has an electronegativity of 2.55 and oxygen has an electronegativity of 3.44. The affinity for electrons is greater on the oxygen, which is why if an extra hydrogen was added in, it would actually go onto the carbon right here. And this right here, if we were to now redraw it, okay, we would now have oxygen with still the double bond with the carbon. Carbon now bonded to the hydrogen, and this oxygen here, it still has a formal charge of -1, which makes sense because HCl2 minus just have a anion and it has a net charge of -1, which is where it's on the oxygen. And as you notice, the carbon no longer has a formal charge of -1 because now it satisfies its original net charge of 0, where it has 4 bonds and no lone pairs, as you can see now. So this right here would be the Lewis structure for HCO2 minus, so hydrogen carbonate ion. That's what they have here. They have, as you see, this top oxygen here has the 3 lone pairs and 1 bond, and then the oxygen to the side has 2 bonds and 2 lone pairs, and then the hydrogen has just 1 bond, 0 lone pairs, and the carbon now has 4 bonds and 0 lone pairs. And that's how we get the minus on the outside, because that's where it is, on the oxygen. So let's move on to question number 7. We have, what is the Lewis structure for C2Cl4? Okay, so for this, once again, we're going to make sure we go over our periodic table. So carbon is on the 14th column. That is 4 valence electrons, but there's 2 of them. So we have 8 electrons it can use from carbon. And chlorine is on the 17th column. So that's 7 valence electrons times 4. So we have 7 times 4. It should be 28. We just double check. 28, perfect. So 28 electrons from chlorine. Add them together, 8 plus 28. We have now 36 electrons we would need to be able to solve this structure. So because carbon has the greatest number of unpaired electrons, that's what we're going to put in the middle. So the 2 carbons would sit next to each other, bonded by 1 bond, and then we're going to add the chlorine. So we have 4 chlorines. 1, 2, let me just redraw this actually. 1, 2, 3, 4. All right, and there will be a reason why I drew it like that, and I'll show you very soon. So chlorine, we're going to start there. Right now, it's sharing 1 of its 7, so it's going to fill out the rest of the octet. 2, 3, 4, 5, 6, 7. Same thing with this one. Same thing with this third chlorine, and same with the last chlorine. All right. Now the carbons, on the other hand, are sharing. Each of them are sharing 3 of its 4 electrons, based on the 3 bonds it currently has. So there'll be 1 unpaired here and 1 unpaired there. The reason why I drew it like this is because in order to satisfy those unpaired electrons, they're actually going to come here and form another bond with this bond. So that's going to be a double bond being formed in the middle. So if we were to redraw this, we would have carbon double bonded with the other carbon, and now we can just put it like that. Or even more specifically, like this. And that's actually, as you can see, what they have in the picture here to the left of me. And this right here will be a Lewis structure for C2Cl4. You can actually check its formal charges. Carbon's net formal charge 0 is just 4 bonds, 0 lone pairs. And that's actually what we have for both carbons. As you can see, the double bond counts as 2 bonds. So you can say, yes, it has 4 bonds and 0 lone pairs. The chlorine, on the other hand, likes to have 3 lone pairs and 1 bond, which is what each chlorine is doing, and that is why it has a formal charge of 0 as well. So this would be the final Lewis structure for C2Cl4. And if you count the electrons, we should have 36, but just to double check, in total we have 1, 2, 3, 4, 5, 6 bonds. That's 12 electrons right there. And each chlorine on the outside is having 6 electrons. That's 12 plus 6 times 4. So that's 12 plus 6 times 4, well, we should be 24. And we do indeed get 36 electrons. So this is perfect. Okay, now let's move on to question number 8. We have for question 8, what is the Lewis structure for hydrogen iodide molecule? hydrogen iodide. Okay. So this is a quick recap. The reason why they named it hydrogen iodide is because it's just following the naming for although technically, because this molecule is considered a polar covalent molecule because it has two nonmetals together. So typically, the official name sometimes will be monohydrogen iodide because it has one hydrogen and one iodine. But because hydrogen typically also kind of twists that rule a little bit, you can just call it hydrogen iodide. In fact, this would actually be it could actually be considered an acid as well because it has a hydrogen to give away. So with that being said, if you actually look at our list of acids, we have here hydroiodic acid. That will be its official name actually. So with that being said though, they're asking for a Lewis structure. So hydrogen is on the first column, so that's 1 electron. Iodine on the other hand is on the 17th column, so that's 7 electrons. In total, we wanted to have 8 electrons. So pretty low number, that's good. So we're going to draw the hydrogen bonded with the iodine, okay? And now we're going to fill out this octet rule. Hydrogen right now is sharing one of its 1 electron, so we don't need to add anything. Iodine on the other hand is sharing right now one of its 7. So it has now 2, 3, 4, 5, 6, 7. This right here would be its supposed complete octet rule. Let's double check. The bond counts as 2 electrons, and then we have 6 lone pairs. 3 lone pairs, which is 6 electrons. So in total, that is 8. Perfect. Hydrogen's formal charge is just going to be 1 bond, which does satisfy. Iodine, on the other hand, would be 3 lone pairs and 1 bond, which it also satisfies. So these two have a formal charge of 0. And that's all we really have to do for this question. This right here would be the Lewis structure for hydrogen iodide, or as we know it, hydroiodic acid. Hopefully I said it correctly. Perfect. And that is exactly what they get. HI. This is correct. Let's move on to question number 9. Okay. This one is telling us now the central atom for, so several steps dealing with different types of Lewis structures and the electron geometry. So for part 1 of question 9, okay, it's telling us that Xenon Difluoride has blank bonding groups of electrons and blank lone pairs of electrons. And the electron geometry of this molecule is blank, and the molecular geometry is blank. Okay? So first, in order to solve this question, we need to first understand what the Lewis structure of xenon difluoride would be. So, xenon is actually a noble gas, so it would be contributing 8 electrons. Fluorine, on the other hand, would be on the 17th column, which is why it would contribute 7 electrons each. So we have 8 plus 7 times 2, which is 8 plus 14. So we have 22 electrons total. So first we're going to draw it out. Okay, we have xenon. All right. And we're going to now put, well, just put it next to each other. Difluoride. Fill out the fluorine's octet rule because this was sharing only one of its 7. That's how we do 2, 3, 4, 5, 6, 7. Perfect. So right now xenon though is sharing 2 of its 8 electrons. So it still needs 6 more electrons. So it would actually be 1, 2, 3, 4. And the reason why I did it like this is because xenon actually has an expanded octet rule. 5, 6. This would be the Lewis structure for xenon difluoride. Fluorine actually already has a formal charge of 0 because, you know, this will be its natural state. Formal charge 3 lone pairs, 1 bond, which is what it does. Xenon is a little bit more complicated because that one typically doesn't form bonds, but the goal here is that Xenon should have 4 lone pairs, okay? But if we were to convert some to bonds, we could actually rewrite this as, because if each lone pair could form 2 bonds, it would be three lone pairs now and 2 bonds, because that 1 lone pair was able to make 2 bonds. So that would be for Xenon, which is exactly what we have here, so that's perfect. So all this has a formal charge of 0, okay? So now it's asking us, it has blank bonding groups of electrons and blank lone pairs. When they ask questions like this, they are actually referring to the central atom, which is actually what they say right there in front of it. So the central atom, how many bonding groups, aka how many bonds it has, that would be 2 bonding groups. And how many lone pairs, as you can see here, 3 lone pairs. So we've answered that part of the question. Now what's the electron geometry? How many total number of groups do we have here? We have 5, okay? So with that being said, with this, the electron geometry, because this will actually be known as sp3d, okay, that's its hybridization. This electron geometry is known as trigonal bipyramidal. Okay, that is the electron geometry. The molecular geometry, on the other hand, okay, funny enough, when you have 2 bonding groups and 3 lone pairs, it would actually be linear. That would be its most stable form, because think of it as the electron lone pairs forming a ring around the xenon and the 2 fluorines sticking out like that on top. So if you look at a plane, this is what it would look like. That ring right here is what I drew as that horizontal line, and this is what we have here for xenon. And it only works, well, there's different orbitals and different hybridizations, but when you have a trigonal bipyramidal electron geometry where there's only 2 bonding groups and 3 lone pairs, that is what we would get for its molecular geometry shape. We actually checked this out with the Vesper theory. So if I went over here and I scroll down, we have 5. Trigonal bipyramidal is indeed the electron geometry. But as you can see here, 2 bonding groups and 3 lone pairs, you actually can see it is indeed linear. That will be its molecular geometry. So now for this question, they're asking us to determine the molecular geometry. So the second part of this question, determine the molecular geometry at each interior atom in the given molecule below. Okay? So with that being said, we're just going to draw each carbon individually and not really draw what it's bonded to, but just the type of bonds. And the last one is an oxygen. Okay? So it's not actually going to be C4, it's going to be around O. So just as a quick note there. So we're going to draw it out. The first carbon we have is this, double bond and 2 single. For this, we can still say that the electron pair, the amount of bonding groups is still going to be 4, okay? Because it has 4 bonds and 0 lone pair. So the bonding groups we can say it has 4, okay? Well, actually, technically, sorry. This double bond here, that was my mistake. It does just count as just a bonding group, okay? Not 2 bonding groups. So this will actually have 3 bonding groups. This is important because this actually allows us to solve molecular geometry. So this is known as just trigonal planar. And because it has 0 lone pairs, it just has the same name of trigonal planar, okay? That would be this carbon here. The second carbon, actually, funny enough, is the same thing. Also going to be trigonal planar because it has 3 bonding groups total. One of them is a double bond, but the other 2 are just single bonds. The last carbon, funny enough, is now like this. So it's also going to be trigonal planar because it also has now 3 bonding groups. So all of these have had 3 bonding groups, okay? So now we're going to go to the one that's clearly different because now it has lone pairs. The oxygen has 2 bonding groups and 2 lone pairs. So in total, the electron geometry, because that's 4 things bonded to it, that would be tetrahedral. But because it has 2 bonding groups and 2 lone pairs, the molecular geometry known for this is called bent. Okay, so just as a review, the molecular geometry for the first carbon, second, and third carbon should all theoretically be trigonal planar, because although there are double bonds, those count as just one bonding group when you're referring to its geometry. Okay, so now with that being said, let's see how we did with the whole question. So exactly 2 bonding groups and 3 lone pairs based on the central atom. So trigonal bipyramidal, which is what we got for electron geometry, and the molecular geometry is indeed linear. So now for the carbons, exactly trigonal planar, which is what we got for the first carbon, okay? Second carbon, also trigonal planar. Third carbon, also trigonal planar. And the molecular geometry around the oxygen, so not C4, but just the oxygen, okay, is bent because it has 2 bonding groups and 2 lone pairs. So this is all correct. So the one distinction I want to stress is that when they refer to bonding groups, even if you have like triple bonds, for example, that still counts as one bonding group, okay? That's why they call it a bonding group, because it could be a single, double, or triple bond that would fall under the same as a bonding group. Let's move on to question number 10. For this, we have write an electron configuration for each ion, okay? So luckily for us, electron configurations for ions aren't too bad relatively. So electron configuration for ions. The ones you have to really focus on are the ones that are typically just break the typical off-ball principle for electron configuration. Those ones are typically found in transition metals because sometimes you have to do some rearranging to make sure you have the right thing. So now let's go ahead and start with oxygen 2-. So we're going to refer to our periodic table here, okay? So as you count through, oxygen is indeed the 8th element. So we want to make sure that we have all the superscripts should add up to 8 theoretically. So I'm gonna start just write it out. So we have 1s2, 2s2, and the reason why I can put that is because hydrogen and helium have been passed, so has lithium and beryllium. And now from boron to oxygen, that would be 2p4. But we're not done quite yet. They say oxygen 2-, so this is not just your regular oxygen. Instead of it being now just 8 in total, we're adding 2 more electrons. So we're actually going to fill the p orbital, and it's going to be instead 2p6. So oxygen 2- is actually what it would strive for in order to end up like neon. This is it trying to complete the octet rule. It's now accepted 2 electrons, filling up its valence shell, and now it's completely satisfied, which is why it resembles neon. Okay, so that would be for oxygen 2-. For Br-, okay, similar thinking here, where it wants to now fill the octet rule and become like a noble gas, but bromine is all the way down here, element number 35. So we're actually going to go through now. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we're on the 4th row now, so that's 4s2. We do pass transition metals, so that'll be 3d10, and now we're back out, and it will be 4p5 currently for bromine. And all these do theoretically, well, should add up to 35. We can actually just double check that just so that we don't have to check for the other ones. So we have 2, plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 5. 35. Perfect. But this is Br minus. So like the oxygen now, we're actually going to fill that p orbital because that is what happens when you add one extra electron. So now the bromine minus resembles a krypton atom. Okay? So now Sr2 plus. So this is strontium. Okay? So if we go over to the periodic table, Sr is right here on the fifth column. So now even further than bromine, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then we have 5s2. So this right here, strontium 38, directly, this is what it would add up to, which makes sense because 4p6, we knew that 4p5 was 35, and then 36, and if we add 5s2, that'd be 2 more, so 38. But we say strontium 2 plus. So for this, it's actually losing 2 electrons. So it'll lose it in its most outer shell to become, kind of like bromine, it's going to become like krypton. Because these two, the most outer electrons, that's the valence shell, are actually now going to be gone. It lost the 5s2. So this will be an electron configuration for strontium 2 plus. So now we're dealing with cobalt 3 plus, okay? So if we refer to it, so cobalt's right here, okay? So it's going to lose 3 electrons. But let's first draw out what it would be. We would have now 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now where it is 3d6. Hopefully I counted that correctly. 1, 2, 3, 4, 5, 6, 7. So 3d7. Sorry about that. Okay. So now this is going to be a quite interesting one. Okay. Because you would assume that if cobalt lost 3 electrons, we just go based on the order. We would kind of want to lose it from the d orbital, because the d orbital and the s orbital are relatively close to where it could lose from it and it would count technically as its outer shell. But let's just say we just lost everything from the d orbital because the one we wrote last. So minus 3, we would now have 3d4. Okay. But here's the thing though, okay? When it comes to transition metals, this is where it gets tricky. The orbitals start to get a little bit wonky, okay? 3d4, that is so close to 3d5 to where all the orbitals are half filled, to where it would actually prefer that. And so that means it would actually take an electron from its outer shell, so the 4s, and this would become 4s1, 3d5, because now we have 2 shells that are halfway filled, okay? This theoretically would be the most stable cobalt it could get, and what it looks like, it would be resembling, if we did minus 3, so 1, 2, 3, this would be kind of like what chromium would do. So that's what cobalt's doing. Cobalt is mimicking chromium, because actually this is what chromium would realistically do if it were out its electron configuration. So now for the last one, copper, and I hope you're seeing in regards to how transition metals do get a little bit weird. Copper, okay, is all the way over here. All right, so it has 1s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, it's 1 away from filling its shell. So with that being said, for this one, we want to make sure that we can approach it the best way. Copper doesn't really lose much from going from 3d9 to 3d7. because why would we then get rid of the outer shell? But the tricky part is here is that the original copper ion would not even be 4s2 3d9, it'd be 4s1 3d10 as a full shell. So now here's where it becomes more complicated. If I put it like this, why would I first get rid of the 3d when I can get rid of the 4s? Because there's only one of them. I don't want to keep going back and forth. So with that being said, we actually would just get rid of this one. And now we would actually just have 3d10 as you got rid of 1, and then it would be 3d9, okay, when you got rid of the second one. So with that being said though, after reviewing that, we'd actually have to go back to the cobalt, because cobalt, just to make sure that we did it correctly, typically in its natural state would be 4s2 3d7, and so if we got rid of the 3 plus, it would go down to 3d4, and then we rearrange. So for this one, I'm going to be honest, I'm not too sure about. And same thing for this copper, just because transition metals do typically go through very different changes, and they definitely break through the off-ball principle based on how the shells are in terms of their energy levels and everything. So let's go over to here, see what our colleague did. Oxygen 2 minus, so then they added 2 more and it becomes like neon, so 1s2 2s2 2p6, perfect. Bromine, same thing, now 4p6 is the end. Strontium gets rid of the 5s2, 4p6 is also the end. Cobalt, on the other hand, yep, 4s2 3d7. Let's see what we get. We get 3p6 3d6. So what they did here was they just got rid of the outer shell completely. It does make sense as well. I was just thinking more so that that's just quite unstable, because I mean, if it could fill this outer shell, it would, but I guess ions do work a little bit differently. So with that, I do apologize. Let's just go over this again. We don't have any more of this. I'm going to leave that here as reference. I'm going to have just 3d6. So it seems that what they're doing here is that when you do get a ion, a cation, as losing electrons, specifically for the transition metals, you want to start from the outside as much as you can, just go in. So yes, the S's, the S shell orbitals, were gotten rid of first. That's how we end up with 3d6. So for copper, before we just go see the answer, let's see if we can apply it here. So for this one, as we said, we start out with 4s2 3d9, right? So if we want to do 2 plus, it'd just be minus the 4s2, leaving us with the 3d9, okay? Even if we change it to where it was 4s1 3d10, which is what copper would actually be as its natural state, we just got rid of 1 here, and then we got rid of 1 here. So we should theoretically get 3p6 3d9 for copper. Let's cross our fingers and hope. Okay, 3p6 3d9. So with that being said though, this is correct, and the lesson here is that you want to start from your outermost shell and just keep subtracting in, and do not try to rebalance it to make it quote unquote more stable. Just keep subtracting from your outer shell as is, okay? And with that, let's move on to the next question. But first, let's take a quick water break, okay? So I'll be just doing that. Okay, we're doing good. Okay. Now we can hop on to the next question here. Question number 11. All right. We have, which of the following is the strongest acid? Okay. So we have CH4, NH3, H2O, and HF. So for this one, we actually go ahead and, in a sense, theoretically add these all to water. So we're going to write down 4 formulas, starting with the CH4. We have CH4 plus H2O, okay? And what does that turn into? Funny enough, CH4, methane, is a non-polar molecule, okay? It just has carbon hydrogens. And because of this actually doesn't even interact with water. We just end up still with CH4 plus H2O. Because all the hydrogens attached to that carbon actually do not want to leave the carbon. They're sharing electrons pretty much evenly, and there's no reason for it to leave. Because we wouldn't get like CH3 minus, and we would definitely not get CH5, okay? Because this CH3 minus, this one right here, the carbon would definitely not even want that, because now it's going to be all over the place. The formal charge is off. It has now lone pairs. It's just a really weird state for methane to be in. So this right here is not even, we can't even consider it. This is not going to be factored in, okay? Now, NH3, when it reacts with water, funny enough, that's how we go from ammonia to ammonium ion. So, if this is now taking a hydrogen from water, okay, that right there, actually, funny enough, makes it a base. So this would definitely not work because of the fact that NH3 ammonia is actually a base. Even based on this formula here as what we got, it wouldn't turn into NH2 minus. It would not want to get rid of any electrons. Similar to the reason of methane, okay, because the formula charge would be messed up, and it just does not want that. So it would actually take on that extra hydrogen, okay, giving us a base. And once you are taking protons from the other one, you are the base, and that is the acid. So this right here would not be the strongest acid because ammonia is actually a base. H2O, this one's a little bit tricky, okay? All right, we have now H3O plus OH minus, okay? So now with this, we do indeed have a base, and we do have an acid, and then we have the conjugate acid and conjugate base. So water can take away a proton from another water molecule. But now the question is, which molecule are we referring to? So technically, it could be an acid or it could be a base. So we're actually just going to do that. We don't really know. It could serve as either. So it really comes down to if HF, hydrogen fluoride, or hydrofluoric, well, actually I don't say that because that would give the answer away, but hydrogen fluoride, we'll see how it reacts. If hydrogen fluoride doesn't even react with water, then technically C would be our best choice because at least some part of it serves as an acid. But let's see what it actually does. So HF plus H2O typically gives us F minus plus H3O plus. And there we have it. We finally have something that's actually giving away a hydrogen. So now that will be our acid and base, and this will be the conjugate base, and this will be the conjugate acid. So based on this, we finally have something that only serves as an acid, not either like the water. So with this, based on what we've written through our formulas, our strongest acid, because it's the only one that actually just works as an acid instead of both, think of HO kind of sitting. That's why HO has a pH of 7, because it kind of sits in the middle. It's neither a strong acid or a base. You can even call it that it's a neutral. Okay, it's neutral pH, but it can serve as an acid or a base. But HF is only an acid, so that's going to be like a pH of around like, maybe like minus pH of 5 or like 2 or something. The point being, it serves specifically one side, which makes it, if we compare 7 and like a 2, for example, we have a much stronger acid in HF. And NH3 was just all on the opposite end. It was more basic, like 12 or something. So we don't even consider that. So that's why the answer here for the strongest acid is D. Okay? Hydrofluoric acid. Funny enough, that would be the official name for it. And you can see here in our acid sheet, HF, although it's a weak acid, yep, hydrofluoric acid would work better as a stronger acid, because if we scroll down to where water is, it's all the way near the bottom, H2O, that is quote unquote the other acid here. Okay, so with that being said, HF should be our strongest one. So CH4 is neither acid or base. Methane doesn't react. Perfect. NH3. Ammonia is actually a base. H2O can serve as either, so we don't know. And HF is the only one that actually donates a proton. So let's move on to the next question, question number 12. We have explain why CH3F is a polar molecule, even though the tetrahedral geometry often leads to nonpolar molecules. Okay, so for this we have CH3F polar question mark, and we have to explain why. So first, let's just draw out its Lewis structure. So carbon will be in the middle, okay, and then we have 3 hydrogens and 1 fluorine. And now you may be thinking, oh yeah, this is obvious because of the electrons, but don't be misguided by the electrons here. The electrons do not always mean polarity. This whole molecule could actually just be sharing those 6 other electrons evenly throughout the molecule. What actually we have to do here is find the electronegativity differences, okay? So, if you go over to our periodic table and we start seeing the electronegativity difference, hydrogen has an electronegativity of 2.2. Carbon has an electronegativity of 2.5, 2.55 specifically. But fluorine, actually funny enough, the strongest electronegative molecule as we know of to this date, has 3.98. So let's look at the electronegativity difference for each bond. The carbon-hydrogen electronegativity difference is around 0.35 for each of those. In fact, around this range is what we actually consider it to be a non-polar bond, okay? These 3 hydrogens and the carbon will be sharing the electrons evenly throughout as much as they can. What about the bond between carbon and fluorine though? 3.98, 2.55, that difference is really big, 1.43. So that means this fluorine here is going to have a lot more say compared to the carbon of who gets to keep the electrons, okay? The higher electronegative number is the one that the electrons will go to, and 1.43, because our typical cutoff for a nonpolar bond is around 0.4. This goes way beyond that. So this is actually known as a polar covalent bond. Okay? So that's one hint there, okay? So now that we have that, we can see here that it's quite uneven. This fluorine will be trying to hog all the electrons as much as it can, while the carbon hydrogens just kind of don't get a say, because fluorine's like, yes, I'm stronger than you all, this is mine, okay? So with that being said, this is how we can kind of say what's going on with our polarity. This is no longer an even sharing of electrons throughout. The fluorine will want to keep hold as much as it can of those valence electrons that we see here, okay? And that is why CH3F is polar. Even though, as I said, typically tetrahedral molecules are nonpolar. In fact, if I did C, F on each one, this right here is also a nonpolar molecule, even though it has polar bonds. The reason being is because of the fact that all the fluorines are trying to keep the electrons, and because they all have around the same amount of power, which is the electronegativity, they all cancel each other out. You're just like, okay, I respect your strength. I know you want to keep your electrons, so I can't really bother you. This right here is considered a non-polar molecule, and this is still tetrahedral molecular geometry. Okay, another example, as we know, is like methane. That one is a little bit more obvious because these are also just non-polar bonds as well, but same thing, they also cancel out. But as soon as you throw in something that no longer cancels out in terms of the electronegativity, even if you throw in, for example, like chlorine, this is also going to end up being a polar molecule. Although chlorine is not as strong as fluorine, it's still quite strong enough to where it can have a say in the electrons it's keeping. Okay, so that's how we get that. Okay, so with that being said, CH3F is polar because the electronegativity difference between carbon and fluoride or fluorine, and because there's no other part of it that would cancel out that electronegativity difference. Okay, so with that being said, let's see what our colleague said. We have a Lewis structure there. Fluorine, 3.98 electronegativity, and that's why it pulls the electrons towards it. Hence how we put this symbol here to show that that's where most of the negative charge would be concentrated. So now question number 13. We have it asking us today, a 9-liter tank at 16.4 degrees Celsius is filled with 15.8 grams of dinitrogen difluoride gas. So that's N2F2. And 2.60 grams of chlorine pentafluoride gas. You assume both gases behave as ideal gases under these conditions. Calculate the mole fraction and partial pressure of each gas and the total pressure of the tank. And then we need to round our answers to 3 significant digits. So the easiest part here we're going to actually tackle is the mole fraction, because we're going to convert those grams as they listed into moles. So dinitrogen difluoride gas, okay, will be written as I said, N2F2, okay? And chlorine pentafluoride is known as ClF5, because penta 5, okay? Now, let's write down also in the information. We have 15.8 grams and 2.60 grams, okay? And we know it's a 9-liter tank. And we know right now the temperature is 16.4 degrees Celsius, okay? So, that is all the information that they've given us. So now let's go through. First thing I want to do, we won't need it now, but just because we are going to use our PV equals nRT formula, the temperature there works in Kelvin. So we have now 273.15 plus that 16.4. So we actually have 289.55 Kelvin. Let's leave that there for now. First thing we're going to do is solve for the moles of each one. N2F2, we need to go to our periodic table to find its molar mass. Nitrogen, there's 2 of them, and the fluorine, there's 2 of them. So that's 14.007 times 2 plus 18.998 times 2. That's nitrogen dinitrogen difluoride, 66.01 grams per mole. Okay, and the ClF5, okay, so that's chlorine, so that's 1 chlorine, so 35.45, okay, plus F5, 18.998 times 5, 130.44 grams per mole. Okay, and just double check we have it. Dinitrogen difluoride, perfect, and chlorine pentafluoride. Okay, so now we're going to find the amount of moles. That's why it's important to always have units, because in order to convert this from grams to moles, we'd actually divide by the molar mass, so that way the moles would be now at the numerator and the grams get canceled out. So that's 15.8 divided by 66.01. Okay, and we get 0.23 etc. Okay, not gonna round just yet because they asked for the mole fraction, and I want to get the most accurate numbers to get that mole fraction. Okay, and now we have 2.60 divided by 130.44. It's going to be quite small, and we do get 0.0199. So the way you calculate molar fraction, okay, and partial pressure of each gas is that you want to have the moles over the total moles, the moles of that gas over the total moles. So we're going to add these two together, the 239, etc., and the 0.199, etc., and we get total is 0.259, etc. Okay, and now we want to divide. So for N2F2, that gas, the molar fraction is going to be, so 3 significant digits. We have 0.239, etc., divided by 0.259, etc., and we get 3 sig digs. Okay, that would be 92.3. The reason why we have 92.3 is because we have to multiply by 100 to get, I guess, that'll be more percentage. I'm going to leave it actually as a decimal to emphasize a fraction. So 0.923. That'll be the molar fraction there. And now for the other one, okay, we're going to have 0.199 divided by that total we found, and we get, for 3 sig digs, 0.0769. That'll be 3 significant digits for that one. So now we found both gases, okay? Alright, so now just to make sure we're not missing anything, we want now the partial pressure of each gas. So what they're asking us to do is find for each one what the P is in the formula PV equals nRT. Okay, so that would actually be P is equal to nRT over volume. Okay, and so I'm going to actually solve it in ATM, and if we actually go over to our units, hopefully it will be there. We want to find out the R value. Actually might be in the physics one, but let's just check this one first. As soon as it loads, and we're actually going to load this physics one as well. So we have units of energy, units of pressure, perfect. ATM, these are just conversions, so hopefully it's here as our formula. Let's see here. Oh no, wait. We just wanted the R value, okay? And we do not have it. Gas constant R, perfect. This is one we'll be using here, the 0.0820575, just so we can get the ATM, okay? We're not, because we're given liters, and we're given the mole, we're given the Kelvin. We're not using the ones with the joules, okay? So with that being said, we have, for each one, it's going to be N, okay? So we're not using the mole fraction, we're actually going to use the actual mole number, which is the 0.239, okay, for the N2F2. So that times the 0.0820575, just to make sure I have that correct. Yep. And now we're going to multiply that by the temperature, which is going to be 289.55. I'm going to divide that by the liters, and the liters, as we discussed, was 9. Okay? And we get, for this one, the pressure is going to be 0.6332. Okay? That's what we're going to get. Alright? And we can actually put ATM as a unit. Okay? Because the mole fraction doesn't really have a unit because it's just moles over moles, so this cancels out. So that'll be for that one. So now for the smaller one, we have now same thing, that times, let me just make sure so I don't mess anything up. Okay. Times everything else that we just did. And we get for this one 0.0526 partial ATM, atmospheric pressure, okay? And now for this one, the last part is going to ask for the total pressure of the tank. For this, actually, if we just follow the laws, we actually just do P1 plus P2, okay? And so the total pressure actually that you'd find when you add these two together would actually be 0.685 ATM. And the cool thing about doing it like that is that you could have also just gone with the total moles for this, and actually you would have still gotten around the same, if not exactly the same answer. So this times everything that we did up here. Okay, let's see. Okay, we get 0.685. So just as a review, we found our our mole fractions here for N2F2 and ClF5. We found out the atmospheric pressure for each partial pressure, and then we found the total pressure, and we rounded each to 3 significant digits. Technically, as you'll see in the answer, they did round 3 and 2 just to make sure that they ended around the same. Just want it to be as accurate as possible. So with that being said, let's go through this question. Yep, the mole fraction, they did get 0.923 and 0.077, which is pretty much what I got if you round it just a little bit. Same thing here, 0.634. The reason why the number is different from mine is only because at this point they are using rounded numbers. As you can see, they use the 0.24 moles, and the same thing here, they use the 0.02 moles, while I kept with the most accurate number. And so that's why the numbers vary slightly. And what they did here, the total pressure, as we could do as well, P1 plus P2, that's how they got 0.687, and that's how I got 0.685. Nonetheless, this is correct. The one thing I would like to stress though is that just like whether it's with math and everything else, you want to save your rounding till the last part as much as possible. I know sometimes numbers do get big. That's why we make sure that we try to go as far as possible. Well, still as far as comfortably possible. You don't want to overdo it, but at the same time, you don't want to be cutting off your numbers too early, because that way you want to get the most accurate result. Okay? So question number 14. Okay. How many liters of a 3.80 mole of K2SO4 solution is needed to provide 82 grams of K2SO4? And recall that molarity is equivalent to moles per liter. So this one, we just need several conversions to find out the answer. So we want to go to liters overall, okay? But that liters needs to account for 82 grams of K2SO4. So that is actually what we would start with here, because we want to go from grams to moles, and then moles to liters based on the molar mass. Based on the molarity we're given. So we have 82 grams of K2SO4. All right, and we're actually going to multiply it by the molar mass given. Okay, so we're actually not multiply. We want to divide. The reason why I say divide is because I want to cancel out those grams units. 174.01 grams per 1 mole. Okay, of the K2SO4. And now, how does our molarity factor in? Recall molarity is equivalent to moles per liter. Right now, our moles is the numerator, but we want liters in the numerator. So it actually divide by that molarity. It would be 3.80 moles per 1 liter of K2SO4. Okay? And the reason why I wrote it all like this is because you should be able to just multiply through and divide through. Okay? Now we have grams cancel out with these grams, and the moles cancel out with these moles. So as I multiply through, the only units I have left should be the liters, okay? So theoretically, this is all we need to do. We would multiply 82 times 1 times 1, which is just 82, but then we have to divide by 174.01, and then divide again by 3.80, okay? So let's see here, 82 divided by 174.01 divided by 3.80. So our answer here to two significant digits, or three, because it's pretty close, we're going to actually have 0.124 liters. That is all the liters we need of this very concentrated solution to account for 82 grams of K2SO4, potassium sulfate. That is all the liters we need. Now let's see if we're correct, if we can approach it with this method. We have moles, 82 divided by 174. We do get 0.47 here as a mid-step. And then we just divide the moles by the molarity, and we do indeed get 0.124. So with that being said, this is correct. And exactly, it's just important that you just watch for your units. The units you want to end up with, make sure it is at the numerator typically, so that way, you know you're going the right way. And now question number 15. Whoops. 15. What is a Lewis structure of ethene? Okay, and they were nice enough to just give us a structure for it. It is just HCCH. So funny enough, there's two ways you can approach this. One, the first way I'm not going to really cover, because that one you need to just know your hydrocarbons, and when you see something that ends with Y and E, it does a specific thing, which I will circle back to at the end. But for now, let's approach this by just drawing out the Lewis structure and filling in the lone pairs and everything else. So carbons, there's 2 carbons, 2 hydrogens. Each carbon is going to contribute 4 electrons because it's valence. Each hydrogen is 1, so in total we should have 10 electrons to work with. So we have H, C, C, H. Okay? So that's what we're going to start with here. Now, hydrogen is already sharing one of its 1 electron. Same with the other hydrogen on the other side. The carbons, on the other hand, are right now sharing 2 of its 4 electrons. So it would be like that, 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 that. So they both have 2 unpaired electrons. So in order to get rid of these and satisfy the octet rule, what's going to happen is that both unpaired electrons are actually just going to bond here, to where now it forms a triple bond. And as you can see here, we've already accounted now for the 10 electrons because there's 5 bonds in total. That is 10 electrons. And this actually would just be the Lewis structure of ethene, okay? And now, going back to what I said earlier in terms of the hydrocarbons, so the rule is that if it ends with a Y and E, okay, that means there's a triple bond present. And that's actually what we have here. Okay, there's 3 types. So usually alkanes, that's what they're called, ANE, implies that it's completely saturated, only single bonds throughout. Alkenes, okay, that one is not saturated. There are double bonds present. And alkynes, which is what we have here, means that there are triple bonds present, which matches perfectly with our Lewis structure, okay? So that is what you would get for ethine, okay? So as you can see here, they go through it, and there you have it. The Lewis structure of ethine is 3 bonds there because it's a triple bond. And now question number 16. Okay? We have draw the best Lewis structure for CH2O. Based on Lewis structure for that, consider the following: the electron geometry, the strongest intermolecular force the molecule would exhibit, and it lists out 3 of them, and then the last one is the molecular geometry. And yes, electron geometry and molecular geometry can be different at times. So the best Lewis structure for CH2O. So carbon is the 14th column element, so that is 4 electrons it can donate. Hydrogen, 1 each, so that would be 2 electrons there. And oxygen on the 16th column would be able to give 6 electrons. So that's 4 plus 2 plus 6. So CH2O. In total, we're working with 12 electrons, okay? Now, because carbon has the most unpaired electrons, we'll put that in the middle. And we have C, H2, and O. So here, the hydrogens are already done, okay? They are sharing one of their 1 electrons. So we don't touch that. Oxygen, on the other hand, is sharing it's sharing 1 of its 6. So we need to add 5 more, okay? 5, there. Carbon, on the other hand, is sharing 3 of its 4. So we just have 1, 2, 3, 4. So that being said, these two here should come together to form a double bond. So what we really have is as the most stable structure, this is what we would get for CH2O. As you can see here, everything is filled as octet rule, and also should be formal charge of 0, because carbon's net formal charge of 0 is 4 bonds, which is what it has. Oxygen, on the other hand, is 2 bonds and 2 lone pairs, which is also what it has. So we're good there. And the hydrogen is just 1 bond, so we don't have to worry about that, because that's exactly what it has. So now for the electron geometry, okay, we need to count how many, pairs it has, whether it's bonding pairs or lone pairs. So for this, it has 1, 2, and here's the tricky part. Even though it's a double bond, it still counts as 1 bonding pair, okay? Because of that, alright, the reason why we did this is now it has 3 bonding pairs. And so the shape, based on this having just 3, its hybridization is sp2, okay? And the shape is trigonal planar. Alright? So that will be the electronic geometry. What will be the strongest intermolecular force in this molecule? Let's look at these, okay? Everything has London dispersion force, so that's technically not incorrect, but I'm sure we can get stronger than that. We have dipole-dipole and hydrogen bonding. Hydrogen bonding, the reason why I skipped dipole-dipole is because hydrogen bonding is a little bit easier to solve. It only occurs when these 3 happen. Fluorine attached to a hydrogen, carbon, oops, sorry, not fluorine. Carbon, nope. It is, yes, oxygen, hydrogen, fluorine, hydrogen, and the last one, nitrogen, hydrogen. These types of bonds here are what they refer to as hydrogen bonds. Unfortunately, none of those are present in this molecule. So even though hydrogen bonding is stronger than London dispersion, there's none here we can see. Now dipole-dipole, that one is a little bit more intricate. That one is based on the electronegativity difference. So between carbon and hydrogen, this actually, so carbon is 2.55, hydrogen is 2.20, so the difference is 0.35. Those type of bonds are typically considered non-polar covalent bonds, so they're non-polar. But the carbon and oxygen has 3.44. So because there is a, let me just do the math, 3.44 minus 2.55, there's a 0.89 difference. We're now in the range of a polar covalent bond. So this oxygen would exhibit a greater electron affinity than this carbon here. Okay? So because of that, the molecule is polar. And so because it's polar, it actually would exhibit a dipole-dipole bond when these, CH2Os pass each other. The more negative oxygen side will be attracted to the more positive carbon side, okay? So with that being said, dipole-dipole is stronger than London dispersion. So the strongest force here would be dipole-dipole. And now the last question, the molecular geometry. This one is a little bit tricky because it's going to be very similar, in fact, actually the same as the electron geometry, because we have 3 bonding pairs, but we have 0 lone pairs. Meaning that because 0 stays the same of 3 bonding pairs, the name carries over to where it is a trigonal planar molecular geometry. So these are the 3 answers we should get. The electron geometry is trigonal planar, the strongest force is dipole-dipole, and the molecular geometry is also trigonal planar. Let's see how we did. So as I drew it, it should be a double bond. Perfect. This is what they should get. A double bond with the oxygen and 2 CHs. There we go. So now, the answer, trigonal planar, that's the electron geometry. Dipole-dipole, correct again. And because it has 3 bonding groups, it's going to be trigonal planar again. So this is correct. And now let's move on to question number 17. We have, which of the following is not a greenhouse gas? We have water vapor. Okay, so which is not a greenhouse gas? We have A, water vapor, okay, B, nitrogen, C, carbon dioxide, and D, methane. Okay, so now with this is more of a conceptual question. We can work through this, but typically it's one of those things where you kind of have to know. But let's try to apply as much logic as we can to these 4. So let's start with water vapor. Water vapor, water is always, just how we have precipitation, condensation, water is always switching states. It goes from liquid to gas, gas to liquid, liquid to solid when it's snowing and such. The point being is that even around you, the humidity, for example, humid places have a lot of water vapor around them. So there is a hard thing to say where there's literally 0 water vapor. That is typically always going to be present in our atmosphere. Okay, so water vapor would not be the choice we'd go with. Nitrogen, I know that there's a bit of nitrogen typically in the soil, for example, but in terms of the gases that we breathe in, it's not typical that you'd hear about nitrogen in the gas. I mean, nitrogen in the air we breathe. Carbon dioxide, funny enough, greenhouse gas, these are like, where plants are held typically, that would be what they usually produce. They're taking in oxygen and producing carbon dioxide. So that would definitely be present there, okay? And now for the last one, methane. Funny enough, this is the sneaky one. Methane is also, I guess, when fruits ripen and such, and things like that, this is actually one of the gases that they produce as they are ripening. As far as I can remember, methane is actually quite present in greenhouse gases. Okay, CH4, and it does have to go through with the whole fermentation procedure. I don't know the formula off the top of my head, but I do know that methane can be one of the products when fruits are ripening, like your bananas and such like that. And the more methane gas present, the quicker typically things like to ripen. That one, I would just double check if I were you. I do think that is the case, but my memory may be a little bit foggy in regards to that. But nonetheless, I would say methane is definitely present. And as I said, the only one that I'm not sure about is nitrogen, because I only hear about it, there needs to be a certain soil concentration of nitrogen, but I don't really hear it about being a gas present, even in the greenhouse or even in the air we breathe currently, okay? So with that being said, as my colleague said, the answer choice would be B. And their logic is, yes, water vapor, carbon dioxide, and methane are among the most common greenhouse gases, and nitrogen is not. So with these type of questions, I do emphasize that when this information is not memorized, we try to apply and go step by step and try to go by just the best choice, crossing out the ones that don't really make sense. So we could definitely cross out water vapor and carbon dioxide. It was just between methane and nitrogen. I only was able to cross out methane because I knew that fact about the whole fermentation, and even that may be a little bit off, but I just was more familiar with methane being present. So for these, whether it's more in the biological realm, I would just emphasize just going through and really reviewing your notes when it comes to greenhouse gases, and just trying to make it as applicable as possible when you talk about each individual gas present. Okay? So let's move on to the next question, question number 18. Okay? We have how many orbitals in the third shell? You can see the answer there already, but let's break it down. If we didn't just know the formula as they give us, or just n squared in n equals 3. So when this is referring to is that when you're actually doing like your electron configuration, they're asking you how many orbitals really are in, like when you have the third shell. So we know that there's 3s, 3p, and 3d. Okay? Funny enough, 3s only has one orbital if you did the orbital notation. 3p has 3. Okay? When you did the orbital notation, that's how you have 3p6, for example, and 3s2. The common thing here is that for every orbital, 2 electrons can fit in there. And in 3d, if you remember, it's 3d10. So it would actually have 5 orbitals. So not only were we able to show it through just using the equation of n squared, okay, we can actually now do it like this as well, to where we have 1, 2, 3, 4, 5, 6, 7, 8, 9. This works as well. Unfortunately, my method has its limits because theoretically there are orbitals that go past the f orbital. So drawing it out only typically works till literally like the 4th orbital, because then we have 4s, 4p, 4d, and 4f, and that would be 1, 3, 5, and f is 7. And if you add them all together, 9 plus 7 is 16, which also makes sense when you square it. But if I said on the 5th orbital, for example, there's some orbitals that we don't really talk about because technically now we're going into like other parts that aren't really covered. But theoretically there we say that thing has 25 orbitals. Where does that come from? We don't really know. Based on this equation though, that's all we can say. So that this is correct, and it is going to equal 9. All right. And now for question number 19. We have draw the Lewis structure of CF2Cl2, and we want to draw all the lone pairs, and we want to use dashes and wedges to indicate the three-dimensionality of the molecule. So there you can kind of see the answer already, but the dashes and wedges would actually be based on what type of molecular geometry we end up having. Okay? So with that being said, CF2Cl2, Lewis structure. Okay? So carbon is 14th column. That's 4 electrons. Fluorine and chlorine are both on the 17th column, so that's 7 electrons each. So 7 times 4, that's 28. Plus another 4, that's 32 electrons we're working with total. Okay? So now with that being said, all right, we want to make sure that we can actually approach and solve this. We will put carbon in the middle because carbon has the most unpaired electrons. And we're going to draw just a bond for each one. Okay? So fluorine, fluorine, Cl, Cl. And we fill in the octet because each of these was sharing one of its 7. So that's why I'm adding 6 on each side. Okay? And now, with that being said though, let's see what we can do. The carbon is already sharing 4 of its 4 electrons, so that's done. So does this equal 32 electrons? Let's find out. We have 4 bonds, so that's 8 electrons there. And we have plus 6 times 4, so that's 8 plus 24. We do indeed have 32 electrons. So now, for this shape, because we have 4 bonding pairs, it's known as tetrahedral. And the reason why this is important is because of these 4, 2 would be kind of on the same plane and won't be sticking out of the page and won't be going into the page. So we would have something like this. I like to draw it like this, personally, where I have these 2 on the same plane. So that would be the 2 fluorines, okay? And then this one right here will be sticking out of the page, and this one, actually, you know what? I like it better like this, where this one's sticking out of the page. I always get confused with this part. This one's sticking out of the page. There we go. And that will be Cl, and this one will be going into the page. That will be the other Cl. So if you kind of rotated it this way to where now the 2 Cls are now the same plane, okay, it'd be now this fluorine is sticking out of the page and this one's sticking, if we rotated it like that, it would actually, you wouldn't even be able to see this. It would actually kind of look like this, and the fluorine would be behind the carbon. That's what happens when you rotate it this way. That's what we've done. So it's kind of like the fluorine into the page back there. But this is not something that's very easy to draw, which is why we have it like that, where we can show one going out and one into the page. This is the best visual structure we can use to where we can show that with the wedges. Okay? And the last thing I would say is that it's important that when you do draw this, that you have the out and in the page as close together as possible. You typically want it like that. You wouldn't want to draw it any other way. Just how they've drawn it here, they show that the chlorine and the fluorine are both the ones sticking out into the page. Any combination would have sufficed. It's just important that you always keep them near each other. So let's just add now the valence electrons. Okay, so that's 1, 2, 3, 4, 5, 6. And there we go. There it is. And this is correct. And now, let's move on to the last question for today. Question number 20. We have, what is a Lewis structure for carbon disulfide? So Lewis 4CS2. So for this one, all right, we're going to make sure that we actually count the right electrons. So carbon has 4 valence electrons. He's on the 14th column. Sulfur, on the other hand, has 6 valence electrons, being on the 16th column. And there's 2 of them. So that's 6 times 2, that's 12. Plus the 4 from carbon, the total is 16 electrons we're working with. With that being said, we're going to put carbon in the middle because it has the most unpaired electrons. So we have now 2 bonds for the sulfurs, okay? And now let's fill out the rest of the electrons. Sulfur right now is sharing 1 of its 6. So it has 2, 3, 4, 5, 6. Same with this sulfur. 2, 3, 4, 5, 6. And you'll see there is a reason why I drew it like this specifically. And the carbon is sharing 2 of its 4. So 3, 4. Okay? So now for this, the reason why I drew it this way is because in order to satisfy the octet rules and get rid of the unpaired electrons, they're actually going to form double bonds on each side. And what I mean by double bonds, an extra bond is added with the unpaired electrons coming together. So now what we have for the structure is CSS. the unpaired electrons are gone, and this would be its most stable form. We check the formal charges real quick. Carbon likes to just have 4 bonds, which is what it has here. Technically 4 bonds, which is just 2 double bonds. And the sulfur, on the other hand, likes to have 2 lone pairs and 2 bonds, which is also what it has. So the formal charge here is 0 throughout. And now let's see if we actually have 16 electrons. There's right now 8 electrons because there's 4 bonds. And then each sulfur now has plus 2, plus 2, plus 2, plus 2. So that's 8 plus 8. So 16 electrons total. This right here would be the Lewis structure for carbon disulfide. Okay, we fill the octet rule. We have the right amount of electrons, and each of them has a formal charge of 0. 16, yep, and then there we have it. The formal Lewis structure is double bonded with each sulfur. So this is correct. Okay. So that was the Lewis structure for CS2. And now, with that being said, I just want to thank you again for joining me this morning. You have a lovely rest of your day. And of all the topics we covered today, if you just had any more questions or just want to go over them, please don't hesitate to contact us through the link below, so that way we can have one of our professional tutors come in to help you with that question. All right. Thanks for joining me in this stream, and see you next time.